Okay, next we have Yan Li from University of California, Santa Cruz. He's a PhD student working with Professor Darrell Long at the University of California, Santa Cruz. His research area is using machine learning to improve computer system performance. His current research project is to use machine learning to discover optimal I/O traffic control rules. He has an AirDosh number of 3. 3? Wow, you know, and you're counting with a thumb. That's cool. I'm going blind. 3. Got it. That's right on, man. So, I mean, you don't really hear people sort of, volunteer that as part of their bio necessarily, unless, you're in a mathematical circle. But my first degree's in math, so props to you. Right on. Anyway, come on up, ladies and gentlemen. Yan Li, let's hear it for him.
So, ladies and gentlemen, thanks for staying here. I think we have only 2 more talks to go, and I know some people have left, and so they're gonna miss this very interesting talk. So you guys are lucky you stayed. So yeah, I'm from UC Santa Cruz. We're a research group. We work on many projects. So, for example, we invented Ceph back a few years ago. Yeah, Sage Will was in the lab. So, but now I'm working on performance tuning using machine learning, trying to use machine learning to solve some of the hard decision problems we met every day in systems research. So yeah, we made Ceph with why Lustre? Because I think this is performance tuning. So we want to find the fastest file system on the earth. So Lustre is the fastest. And we want to make the fastest faster. So that's why we pick Lustre. But actually, I think I have to say, compared to everybody in the room, I probably knew least about Lustre. So this talk is more focused on the research part and how we're doing with Lustre to make it, to use machine learning to manage the traffic of Lustre. All right. So the problem, the challenge, we want to provide consistent performance at peak times because we observe that with a given system, when you have more clients doing very heavy I/O, actually the performance goes down. So the aggregate throughput actually goes lower when you have more clients. So why is that happening? Because we observe that actually there's very severe congestion and contention happening at the server and the client or at the disk drive, the OST. So, and for example, this is a throughput chart showing the client throughput of just the 5 nodes accessing 5 servers. So you can see that these lines go high and low very fast, and also the performance difference between clients also significant. This can be very bad if you want consistent performance over different clients. Right? So, and also this is a hard problem because the congestion can occur anywhere in the system. It may occur on the network switch, may on the storage server, may on the disk drive. Right? So it's actually very hard to know where exactly contention is happening without doing a lot of measurement and benchmark. So this is always a hard problem. Think about this. This is a kind of a traffic that you are expecting in a server. So like the server is kind of like without a traffic control system. These cars will eventually get through, but not in a very efficient way. So this is a problem we're trying to solve. All right, we're trying to improve the throughput of fairness during congestion. And we want to provide end-to-end coverage. We want to be able to handle the congestion occur at the client, the server, and also the OST at the same time. Because it's very hard actually exactly to know where this congestion happens. So we want to handle everything. So and the last one is we want this to be fully automatic. It requires as little human supervision as possible because we know the system is always changing. And we don't have a lot of time to tune for a specific workload. Just imagine, for example, you deliver a shining new system to a customer and they say, hey, this is great. So here's my workload. Try to see how fast it can run. And yeah, you don't have like a few days to like build a model to understand their workload, right? You just need a very efficient way to tune for this specific workload. So ASCAR, our research project, is designed to do this. You just throw this workload to this machine learning tool and let it run for like a couple of hours. This tool automatically figure out the best traffic control rules that they can do to make this specific workload run faster on this specific system. So that is the purpose we're doing this research here. So we know that actually there's a lot of different ways to solve the contention problem. For example, there's, I think people are doing the traffic rerouting. If they detect the contention happening on this device, they reroute the traffic somewhere else. And also there's the work on NRS, so the network package scheduler that can also somehow solve this contention problem. But we're trying to attack this problem from a different way. So because we observe that rate limiting on the client side can actually efficiently improve the aggregated throughput if you done it properly. So another reason we want to do this using rate limiting is because this is easy. So I will show you later. Actually, we did very little change to the client. So this comparing with a very intrusive change like to relocating traffic and the network scheduler, this is very little change and can be easily deployed along with other contention management solutions. So actually, I know, sorry, I'll just talk about. So the first challenging about this rate limiting thing is where is the sweet spot? So what is the optimal spot you want to limit the performance? So say, if you set the rate limit too low, it's obviously wasting system resources, right? If you set it too high, it's not very useful. So you need to find a sweet spot. So this specific workload runs on this specific system. You have to set this exactly spot so that the real throughput can be increased to match the ideal throughput. I know some people like from IBM has been working on this on GPFS. And also, there's a lot of work done on network research on congestion control. So usually, the kind of solution is you have to use like a slow start and fast fallback. You have done research in networks, you know this kind of an algorithm. So, but the problem is, how slow is slow? How fast is fast? You have to do a lot of benchmark, just trying to figure out the exact parameter that can fine-tune this specific workload. Right? So if you want a machine to do this, currently the existing solution requires communication, a lot of communication between clients. So if we should fall back, everybody should fall back. If guys, we want to increase the throughput, everybody should increase. This kind of communication is actually, it's very bad if the network is already congested, right? And also, this kind of communication can grow at like a O(n) squared, so it's not very scalable, and it doesn't work well with a highly dynamic workload. So we're working on this idea called ASCAR, Automatic Storage Contention Alleviation Reduction. So it uses actually a very simple notion of a client-side rule-based I/O rate control. And so every client following some traffic control rules that is pre-deployed before running this workload. There's no need to talk to anybody when this workload is running. And you see the trickiest part is here using machine learning to figure out what actually is the best rule for this specific workload. This is a component of the ASCAR prototype. So actually, the only change to the master file system is here. We add some traffic controllers between client and servers. So this is a extra node we added to the system. This manages the deploy and a deploy of traffic control rules. So when you have a new job running up, so we deploy a couple of traffic rules, and then you're good to go. When this workload is running, there's no need for the client to talk to this management node. All right, so what does the traffic control rule look like? So actually, the traffic control rule is very simple. So we know that, for example, when you detect the congestion is building up, we're running some statistics. So we detect, oh, these statistics are increasing within this range, so we should slow down. Then, right, this is one rule. And you will have another rule that says, oh, the congestion are freed up, so the values are getting lower to this range. Now we increase the rate limit. So traffic rule is actually very simple. The mapping between congestion statistics to actions. And we're measuring a few statistics here is the three blue ones, EWM, ACK, SEN, and PD ratio. So the first two are exponentially weighted moving average of the gaps. The first is the gaps between the acknowledgement you received from the client, a client received from the server. And the second is we embed the send time in the RPC request. So when the client received an ACK from the acknowledgement from the server, it also can know how long the server takes to process this request. So this is the second exponentially weighted moving average. The process time ratio is even simpler. It is how long the current It's the ratio between the current processing time versus the minimum processing time we have seen so far. So for example, if we have seen the minimum processing time for requests is 1 microsecond, and now the server is taking 2 microseconds, then this ratio is 2. So this ratio is always from 1 to larger values. And the action here, we're actually controlling two things. The first is the IOQ depth. Here I call it congestion window. It's more like a general term. But for IO work, the IOQ depth is actually, to be more specific, in Lustre, we're tweaking the maximum RPCs in flight, MRIF. So for example, when we see there's congestion building up, we shrink this congestion window. When we see the congestion is freeing up, then we enlarge the congestion window. So, and another mechanism will also set a heart rate limit. So we're doing two kinds of control. One is IOQ depth, another is heart rate limit. All right, so the next one is how we generate the traffic control rules. It's actually quite simple. So just follow the general human way. You generate a bunch of candidate rules. You think, okay, this may be an interesting value, and we try them one by one on the real system, and then we pick up the best one. And then we further fine-tune this specific one. This is actually very simple, just automating this human process by using heuristics and some machine learning. All right, this is give you a very practical example of how we generate a traffic control rule from nothing. This is the beginning, showing just one rule that maps to action. So you can think about this as like a 2D space, right? The x-axis is the ACK EWMA, the y-axis is the PT ratio. So in the beginning, we map these two values, all these values, to one action. This is just one rule, right? So in reality, actually, we're using 3 congestion statistics. So this is more like a 3D space. We map, in the beginning, everything in the 3D space mapped to one action. Of course, this is not very interesting. But later, we will actually divide this single rule into more rules. Okay, so first, we want to find the best value for this MB and tau. So MB controls the IOQ depth, and tau is the heart rate limit. So what we do is we start from some random value, and we move geometrically away from the existing value. So MB and tau. So here, because this is starting from random value, the existing values is not very interesting. So we take different combinations for this value, MB and tau. We try them, generate candidate rules using this value, we send them to the client to test this on the real workload, and we find that, okay, this value works best for this specific workload. And then the next step is we want to generate more rules. We want not only fine-tune this parameter, but also we want to increase the complexity of the structure of the traffic control rules. So the next step, we splice it into 4 disjoint rules. So we splice that at the values that we have observed at the average value in the past. So we splice at the average value observed for ACK EWMA. The purpose here is we want the 4 new rules to have an equal chance of being wrong. So we take the average, slice it into 4 different rules. If you have like 3 congestion states you are measuring, then you have to splice into the 3D space, you splice 3, then you get 8 different disjoint rules, right? And then we measure, okay, these 4 rules, which one is the hardest one? Which one is being triggered the most often? We found that the top left one is being triggered most often. We focus on measuring that one, and we do the same thing here. We move geometrically away from the existing value of MB and tau. So why geometrically? So by doing this, we can both fine-tune from the existing value of this rule. We can try to search around these existing values carefully to see if there's a better one around. And also, even though fewer and fewer, we're also checking other values further away from the existing value. So this is like an optimization problem because it's like a random restart hill climbing. So we want to find the local maximum, but also we're expecting to find some other maximum in some further distance. So again, we measure back to this, we measure the performance optimizing the top left one. We found out, okay, by changing the value to this, actually it increases system performance even better. And now we got new values for this one. And again, we split into even more rules. After splitting that one, these rules are no longer the hardest. This one becomes the hardest, and then we repeat this process. This is an iterative process that we do it over and over and over, you can see. So this is how we generate traffic control rules. All right, so we did a prototype and for Lustre. And so the only change we need for the Elaster itself is we patched the Elaster client. We added some mechanism for reading in the traffic control rules and to calculate these congestion statistics on the fly and take actions according to the traffic rules. Well, I have to say, so we are a poor lab in the school. So we don't have the shining hardware you guys have in your labs and before you deploy to our clients. So we're using a very small system. But I think this prototype demonstrates that we can get very interesting results. So if you have a better hardware, you want to try this, you think it would be benefit to optimize your system for specific workload so far, you can just, we can talk and we should do evaluation together on a larger scale. All right, so this is the graph I just showed in the beginning of the talk. This is a very bad running wild client. And actually the right side, this graph shows when we apply the best traffic control rules discovered by ASCAR. You see, it not only increased the average throughput, it also lowered the speed variance at the same time. So we think this is really fascinating result. And this is a summary of all the workload we have evaluated so far. And we have to say these are all synthetic workload. We don't have the real application workload. So this graph is probably a bit hard to read, but the x-axis is the change in terms of in percentage of the throughput. So we move further to the right. So this shows using ASCAR can actually boost the performance of this workload. And the y-axis shows the lower speed variance. So what you want to move the workload is either to the right, or if at the same time you want lower speed variance, to the lower right corner. So actually we apply, so here are two different kinds of nodes. The first is blue dots, and the second red dots. The blue dots shows that we only care about throughput. And the red dots is we're trying to find a balance between increasing throughput and lower variance. So for this workload, we can see these three actually get best performance boost. Their throughput has been increased by like 25 to 35%. If we don't care about if we don't care about even higher variance, but at the same time, if you want lower speed variance, we can sacrifice some throughput, but we still get something like a 15, 20% increase. But you can also lower speed variance by almost 50%. I think this is a very interesting result. All right, so the prototype shows that can increase the performance of all the workload, literally all the workload we have tried. Some not as good, like the read-heavy workload, we can only increase by like 2 or 3%. And some write-heavy workload can increase by 30, 35%, 36%. Yeah, so they work best for the write-heavy workload and can also lower the speed variance at the same time. There's some limitations, I have to say, because this is a very early prototype. The first is that currently the training process is offline, so you have to occupy the system to run ASCAR to train this rule for a couple of hours in order to discover the traffic control rules. And it has to retrain, load different rules for different workloads, because obviously this system is just designed, it's never meant to be general, to generate traffic control rules that can cover all the workload. No, it's just designed so if you are running this workload over and over again, which I believe is true for many HPC systems. So this can implement a way to discover the traffic control rules just to optimize the system for running this specific workload. And also, it's very good for benchmark and evaluation because this kind of a workload can be very predictable and stable. All right, actually we're doing active research into many related ways of using this project. So the next one is we're looking into ways of handling a new workload without training. So we want here, so let's say we have a database of existing workload characters and the already discovered traffic control rules. Now you give me a new application. And then we need to figure out a way to see which one of the known workloads traffic control rules work best with this new workload, right? This is more like a workload classification problem. So the first thing we need to do is find the right features. We have done a ton of work on this thing. We need to find the right feature that can measure the workload's pressure. Somehow, conceptually, it's like the pressure on the lowering file system, right? And if different workload can show a similar pattern of pressure on the lower file system, then maybe we can apply the same traffic control rules. But however, many existing work using for workload classification use the percentage of a random I/O of read and write. So, but we discovered this kind of feature is not enough. So for example, two of this workload all have like a 75 sequential and 25 random workload. However, they are very different. You can totally imagine, even though with only 25 random workload, the lower one is having much lower pressure on the system because it's easier to handle. It's have a long sequential write, right? And also it's the same thing. So consider like 60% read and 40% write, right? So there's many different ways for doing workload that has 60% read, 40% write. So what we discovered is that we're using the average size of the sequential ops, the actual sequential read or sequential write, and also the average size of the positional gap and temporal gap between the sequential ops. So for example, all two workloads have the same read to write ratio, 60%, 40%, but they have very different average size of sequential read and sequential write. So we found that this kind of parameter can be used as a very good way to characterize a workload in terms of applying traffic control rules. So again, here the goal is to see if we can, for new workload, we can run a small measurement, a small trial run, and gather some characters to some features to see what is the best candidate workload to, what's the best candidate traffic control rules to apply. And we actually discovered that this is more like applying traffic control rule and predict the performance of a new workload. We discovered using this regression trees actually can be very efficiently predicting the new workload's performance. And we found that the most important features in terms of applying traffic control is the read-write ratio and the read size. So we did a evaluation of hundreds of different workloads. We found that using the set regression tree, we can actually find very good results in terms of the first one's correlation coefficient is 0.8. So the best thing you can get is 1. So 0.8 means like we can 80% of chances successfully predict the new workload's performance using the existing traffic control rules. So maybe you guys have got bored about this math stuff, but the gist of the talk is actually very simple. We discovered traffic control rules for existing workload, and now you have a new workload. We can very efficiently, 80% precision, predict the new workload's performance using the old workload's traffic control rules. All right, this is actually not a conclusion because we believe this is just the beginning of some very interesting project, because applying machine learning obviously can help us to solve some very hard decision problems in systems research. And ASCAR shows that only needs client-side change. There's no need to change the server. There's no need to change the servers. I think this is a very good way that can help us evaluate the system, because changing servers, many places is resistant in patching their servers. So we only need client-side controllers. It can be easily deployed to work with existing servers, and there's no need to change hardware either, and it can handle very highly changeable workload. It's work conserving. It's not like a scheduler system, when it's not properly configured, can waste resources. ASCAR never wastes resource because it's a work conserving traffic control system. So currently we have the patch that works for Lustre 2.4, and we're also working on porting this to 2.7, 2.8. So we're looking for collaborators to try to evaluate this on a larger scale, because we know that our evaluation was very simple. So again, so we have published a paper, and we have released the source code here on this website, ascar.io. But the source code may be not very useful even though we publish it, because the system is so complex to set up at the current stage. So if you're interested in knowing more about our research about this project, please just come and talk to me. We can chat about that. So, and at the same time, I want to let you know our lab is also working on some other related research project. So for example, one part of ASCAR is, so we have to measure the performance of a system, right? So it be it Lustre or Ceph. So because this is a cycle. You tune the parameter, you measure the performance. If you want to accelerate this cycle, to make this cycle go fast, then you have to make each step as short as possible. So we're doing on a project, a pilot, that can actually help you to use a lot of statistics magic to get the precise performance measurement with a very precise confidence interval in the shortest time possible. So you can try more parameters in the fixed time period. So this can be very good performance tuning. And also the next research project we're working on is we are actually writing a simple tool based on the pilot I just said that can try different combinations of parameters. For example, the other parameters other than the maximum RPC in flight, there's many parameters tool in the system. This tool can actually go over all the different combinations of these parameters and see which kind of a set of parameters can best work for a specific workload. So yeah, there's a lot of interesting going on in our lab. So come and talk to me if you want to know more. So yeah. Talking about ASCAR, the one thing we want to do is to make it actually online, because currently it requires an offline training process. So to make it online can actually work along with real applications. So you don't even have to have a training time anymore. So you just deploy ASCAR and can automatically work on existing workload by trying new rule on the background. So I think that is a long-term goal we're shooting for. All right, so that's it. I have only 4 minutes left. Thank you.
So in the run you did where you were using, you posted the two graphs side by side where you were using the rules. Do you have any idea how many times during that you changed from, essentially you tweaked the value during the run?
You mean how many times I tweaked the value?
Yeah.
I probably tried, I think it's thousands of different rules.
Well, I mean, once you had the rule set and you did the run, how many times did essentially did a client say, oh, I need to change RPCs in flight from 13
Many.
to 14?
We're doing basically, I think, once or twice every second. So in the paper, there is a graph shows how the I/O depth and the rate limit changes over time, along with the measured congestion statistics. I think it's the last 2 pages on the paper. Thank you.
Thank you for this nice talk. Regarding this optimization problem, you said you do hill climbing, right?
Random restart hill climbing.
Yeah, so you're error prone, so you can stuck in local minimas, right?
Random restart.
You cannot, yeah, well, but haven't you considered any like global optimization method, like simulated annealing from the physics world, or like a genetic
annealing
algorithm?
is actually on our radar. I just need the time to write it up and find a better system to value this idea.
Because this random restart is like the most, well, not naive, but the most intuitive approach, and then do like a hill climbing and go down and then stuck in the local minima.
I agree. In published literature, we know annealing is actually working better than random restart hill climbing. Right. We know that, yeah, but it's just harder to implement.
Okay. And the second question, you said it's an unsupervised learning problem. Is that right? Because it's it's a classical regression problem where you can use like Gaussian processes, or I don't know, you could even use like a neural network and have the output some score, some real value score, and then you can also switch immediately to an online
Yes, after Google's DeepMind AlphaGo defeated the professional Go player, there's a lot of discussion about deep neural network going on. And actually, we're actively looking at ways of using deep neural network plus policy network and reinforcement learning to better optimize this process. But again, the challenge for using neural network in system research is it's really hard to generate a large enough data set. So that is a very tricky question. So yes, we're definitely looking at that direction, but at the same time, we want to first make it online. Then we have access to unlimited training set, right? Because the system can run at the background. We were having real production, maybe not production, but testing system running. So that can give us a very large amount of test data, so we can use that to train neural network. So the first step, we bring this from offline training to online machine learning, and then we'll open the door for trying many different things.
Okay,
but thanks for the input. This is a very interesting idea.
So it might be a naive question, but you develop training rules for specific workloads.
Yes.
How would you automatically know which rules to apply to a given application? Do you measure, like use the binary name and then run it, or is it like stored per user, or how do you decide which rule to apply?
There's many different ways. So the simple way is to use just the job scheduling information from the job scheduler. And also, I think on the developer day when I gave this talk on, someone mentioned we can actually use the file name, because it is probably known that the way to access a file is very fixed, because it's for one application, for one purpose, right? And also, actually, what we're doing is we're actually monitoring the features like the average sequential read and write size and the gap, the temporal and positional gap between these sequential writes. We're actually doing that calculation, and we're running that through a classifier, the decision tree, and to see if the current workload is changing or if it's from a known workload. So actually, we're taking the more complex approach. But I think with the production system, we will have the job scheduling information, we have the file name information. That can be more easily handled than just having to measure the workload's features.
So file name might not be a direct indicator, because you can run the same file name with different input decks that will generate different I/O patterns. At Oak Ridge, we have developed a tool that extracts the I/O signature of a given application.
Yes, that's what we're doing now.
Yeah,
Yes.
I can forward that link to you if you're
Okay,
interested.
thanks.
I guess one of the things that struck me about this, we've done a lot of work with wide area networks, and there are a great deal of parameters that you can really screw up. And one of the things that we've been looking at, are what are acceptable applications that you could compute in place with. The Cray guys were talking earlier about using InfiniBand to compute in place, and this is something we've been doing across, long distances. Do you think that using these techniques, this would be something we could optimize, wide area performance?
This is an irresponsible answer. Why not?
Well, thanks. That's all I wanted to hear, because, hope is really, where it's at. It's springs
this is
eternal.
early stage research product, but I see there's no reason why we can't do that.
Cool.
Let's just try it. Give it a try.
No, well, right on. Let's talk.
Yeah.
Thanks so much, Yen.
Thank you so much, Sims.
Let's give him a hand.